guys, this is Nandish from Aja Physics. Today in this video, we will see the concept of the reduced mass, when to use it and what is the advantage of using this reduced mass. That is what our concept. For that, we will consider two particles. Assume that masses of these two particles are m1 and m2. Initially, they are separated by a certain distance d. Okay, so assume that they are separated by the certain distance d, and this system of two particles is completely isolated, which means there is no external force acting on the system of two particles. This is completely isolated. But the one thing is, these two particles can exert mutual gravitational force of attraction on each other. That is possible. That gravitational force only between them is called as the internal forces of the system. Now I will call this the gravitational force acting on the second particle by the first particle is F21. Similarly, the gravitational force acting on the first particle by the second particle is F12. So from third law of Newton, okay, from the laws of motion, I can say that their internal forces, they must be equal and opposite in their directions. Because of the equal and opposite forces acting on these two particles, their momentum when they are moving because of these forces must be exactly equal and opposite also. Okay, so to conserve the linear momentum, and the Newton's third law is satisfying between these two objects. That is what our assumption. Now the question is how to calculate the total kinetic energy of the system. That's very simple. The total kinetic energy of the system is equal to half m1 v1 square plus half m2 v2 square. Here this m1 is the mass of the first particle or the first object, and m2 is the mass of the second object or the second particle. v1 is the velocity of the first particle and v2 is the velocity of the second particle. But the question is, from which frame of references we have calculated this v1 and v2, the speeds of the particle. From which frame we have calculated? The frame is, from which we have calculated this speeds or velocity is, there are two frames are possible. One is the frame which is fixed at the center of mass of the system of these two particles, and the second one is any laboratory frame. Okay, I can write that as a laboratory frame of reference. So by using these two frames of reference, I can calculate the total kinetic energy of the system by measuring the velocity or the speeds of these particles from either any one of these frames of reference. This process is quite longer and it is also risky, because we have to choose a proper inertial frame of reference and from which we are calculating the speeds of these two particles, and then we have to calculate the total kinetic energy by using this equation. Now, how if you can calculate the total kinetic energy of this isolated system of two particles by having only one term in the kinetic energy equation? That is also possible. Okay, so let me write that equation so that how I can calculate the total kinetic energy of the system just by having one term. Okay, so I can also write the total kinetic energy of this system. The system of two particles, they are attracting each other and they are approaching each other. The total kinetic energy can be written as half m1 m2 divided by m1 plus m2. I will keep this expression, this quantity inside the bracket, multiplied by v square. So what is this v? The velocity of which particle? That's very simple. This v is going to be the relative velocity or the relative speed of one particle with respect to other particle. This is going to be the relative velocity. I hope you know what is it. And this expression which is inside the bracket is actually called as the reduced mass of this system of two particles. I can also write the same equation as k is equal to half mu and v square. This mu is nothing but m1 m2 divided by m1 plus m2. This is called as the reduced mass. So this equation is much simpler. We no need to choose a frame of reference, because to calculate the speed of these two particles, as we have done in the last case, this is going to be the relative velocity of one object with respect to another object in that system of two particles or the two objects. Okay, so the frame of reference in order to measure this velocity is any one of this particle, and this mu is called as the reduced mass. So the reduced mass is equal to it. Now the question is the difference between these two particles. The very simple difference is there are no two velocities in this expression, as we have seen earlier, and there is no need of choosing a proper inertial frame of reference to measure the velocities. Okay, the risk is smaller, or you can easily calculate the total kinetic energy by having this equation. Now what is this reduced mass basically will give us? That is very important to understand here. Reduced mass of a system of two particles, and assume that the system is isolated, is basically gives you the effective mass of the system of two particles which is actually participating in motion. Okay, that will be this reduced mass of the system of two particles, isolated system of two particles. Okay, so let us understand this reduced mass. The concept of reduced mass will actually very helpful in calculating the total kinetic energy of system of two particles by taking an example. So to understand this reduced mass, this can be taken as to calculate the total kinetic energy of system of two particles. I'll go with an example. Here in this example we have two charged particles. One is, assume that this is positively charged particles which is heavier, and this is a negatively charged particle which is very small in its mass. I'll call the mass of this positive charged particle is capital M, and mass of this negatively charged particle is small letter m. Initially they are separated by the certain distance d. Now they, because of they are different charges, they will start attracting each other, the electrostatic force of attraction, so that because of the Newton's laws of motion, as I have told you already, this positive charged particle will going to attract the negative charged particle with some amount. I will call that as F2, the force acting on the second charged particles. Similarly, this particle, the small negative charged particle, will also attract the bigger one, the positive charged particle, with the same amount of force but in the opposite direction. You can call that as F1. But here we have a small difference from the problem what we have taken earlier. Initially those two particles or the objects what we have taken, they were having a masses m1 and m2. There was no much difference in their masses. That is why both of those particles or the objects, they were moving, they are approaching each other with approximate velocities v1 and v2 measured from the lab frame. So here the problem or the situation is quite different. They are exerting equal and opposite forces on each other, but here only the small negative charge will be moving. This will be almost at rest. I cannot say it is exactly at rest. This will also have to move because it is acted upon by the same amount of force as this is exerting on the negative charge. Okay, this will be also in motion, but that motion is almost negligible. Its velocity can be almost taken as zero. Why it is so? The question is why it is so. It is because they are exerting equal and opposite forces. They have to conserve their linear momentum. So what is linear momentum? Linear momentum is nothing but the product of mass and this velocity, is it not? So here these two particles, because of the mutual equal force of attraction, they have to move with the same momentum from the opposite direction. That is what the conservation of linear momentum. This will be having very smaller mass and its velocity will be greater, and this will be having larger mass already, so that its velocity will be very less. When very less velocity, its motion is considered to be neglected, or it is almost having zero velocity. So guys, in this example what we have taken, one is very small and the other one is very big when compared to other. Okay, in this case only one particle is actually in motion in this system of two particles, is it not? So that the effective mass which is actually participated in the system of two particle is only the mass of this small negative charge, because this is almost at rest to conserve the linear momentum of the system from the Newton's third law of motion. So now I will apply this same equation. The total kinetic energy can be calculated over here also. Okay, so the total kinetic energy is going to be half this m1 m2 divided by m1 plus m2. So here m1 is nothing but the mass of the one charged particle and m2 is the mass of the other charged particle. In place of m1 I'll take the mass of the first particle, the positive one or the bigger one, and in place of m2 I will take the small letter m divided by m plus m multiplied by the v square. This v is nothing but the relative velocity of these two objects. I mean the relative velocity of this negative charged particle with respect to the positive one, or the relative velocity of the positive charged particle if you are sitting in the negative charged particle. Okay, so now you can see this according to this example what we have taken in this case. This m, the capital letter m, the mass of the charged positive charged particle is much bigger when compared to the small charged particle. It's very small, just like the big nucleus and a small electron. Okay, now I can put this approximation in this equation. So what we will get, the total kinetic energy is going to be half. So here I'll write both the masses divided by, you can see in the denominator of this expression, this m is, the small letter m is very small when compared to this capital M, which means this denominator is approximately going to be capital letter M only. Why it is so? Because this is very small. Even you are adding a small quantity of mass to this bigger mass, there is no change in the value of the denominator apart from this capital M. Okay, because this m is very small, so I can only consider the capital letter M in the denominator multiplied by the relative velocity is v itself. Now what I can do, I can cancel this m and m. The total kinetic energy is half small letter m and v square. So guys, you please observe here, this is very important step. In the example what we have taken, okay, I mean the system of these two particles, one is the positive charged particle and the other is the very small negative charged particle. The effective mass which is participated in motion is actually electron only. I mean this small negative charge only, not this bigger positive charge. So that is what we are arriving at this equation over here. So even by using the concept of reduced mass, I mean the total kinetic energy can be calculated by using half m1 m2 divided by m1 plus m2 into v square. Even by using this equation to calculate the total kinetic energy of the system, but when you simplify this by taking this approximation, you are arriving at this equation, is it not? The total kinetic energy of this system, this isolated system of two particles, is only the kinetic energy of this small negative charge particle only, because this is not moving to conserve the linear momentum. We are arriving at the same thing. So therefore the concept of this reduced mass is very helpful in calculating the total kinetic energy. Okay, so I hope you guys understand this concept of reduced mass, and thank you for watching. In the next video, I will be solving some problems which are based on the reduced mass concept. Thank you.